Hi all. So in this video we are going to discuss about the static error constants. In the previous video we have learned what is a steady state error. Okay. So here we are going to find some relations between this steady state error and some static error constants. Okay. So normally when a control system is excited with the standard input signal like step, ramp and parabolic, the steady state error may be 0, constant or infinity. Okay, that is, if you are giving a standard test signals to a system, the steady state error may be 0. Okay, it may be 0, or it may be a constant value, or it may be an infinite value. Okay, so actually the value of steady state error mainly depending upon the type number. Okay, type number and also the input signal we are giving. Okay, so it is mainly depending on the type number and the input signal we are giving. Okay, so for a type 0 system, listen carefully, for a type 0 system will have a constant steady state error when the input is step signal. Okay, that is if you are having a type 0 system. Okay, type 0 system means suppose we can write as just like s plus 1 by s plus 1 into s plus 2 into s plus 3, like that. Okay, so this is a type 0 system because the number of poles in origin is 0 here. Okay, here the number poles are s equal to minus 2 and s equal to minus 3. Okay, so there are no poles at origin, so it is a type 0 system. So for a type 0 system, if you are giving a step signal, okay, if you are giving a step signal to the system, we will get the steady state error as a constant value. Okay, the steady state error will not be a 0 value, or it will not be an infinite value, so it will be a constant value. Okay, and also for a type 1 system we'll have a constant steady state error when the input is ramp signal, or we can call this a velocity signal. Okay, that is if you are having a type 1 system like that, that is s plus 1 by s into s plus 2 into s plus 3, like that. Okay, so here s is there, s time is there, that is we are having a pole at origin. Here the value of s is 0. Okay, the value of s is equal to 0 here, so we are having a pole at origin. Okay, so for a type 1 system we'll have a constant steady state error when the input is a ramp signal. Okay, that is if you are giving a ramp signal for a type 1 system, the error will be a constant value. Okay, and also likewise we can say for a type 2 system we'll have a constant steady state error when the input is parabolic, or we can call it as an acceleration signal. Okay, so type 0, type 1 and type 2. Okay, so for these three cases mentioned here, the steady state error is associated with one of the constant of these three, that is position error constant, then velocity error constant and acceleration error constant. So these three are called static error constants. Okay, so the first static error constant is Kp, that is positional error constant. The equation for Kp is very simple. Kp is equal to limit s tends to 0 into g of s into h of s. The question, if you are having the value of g of s and h of s, by simply applying the limit for s equal to 0, s tends to 0, we can find the value of Kp. And also the velocity of the constant Kv will be equal to limit s tends to 0 s into g of s into h of s. And the acceleration of the constant K is equal to limit s tends to 0 s square into g of s into h of s. So you have to learn all these three equations. Problems may be asked in the university questions. Okay, so Kp, Kv and Kr are called the static error constants. Okay, and here we are going to check the steady state error when the input is unit step signal. Okay, that is the input is unit, that is we are going to find something, a relation between the static error, steady state error and the static error constants, that is ESS with the Kp, Kv and Ka, like that. Okay, so first we are considering a unit step signal. Okay, that is steady state error when the input is a unit step signal. So we know that the steady state error equation for steady state error is equal to limit s tends 0 s into r of s by 1 plus g of s into h of s. This is the equation here. Okay, and we know that if the input is a unit step, the value of r of s will be, of course, it will be 1 by s. Okay, because it is a unit step signal. So by just substituting the value of r of s here, we will know that s and s will be cancelled, and we will get it as limit s tends 0 1 by 1 plus g of s into h of s. Okay, and we know that these ones are constant, so it is same if you are applying the limit to the g of s into h of s only. Okay, so we can simply write 1 by 1 plus limit s tends 0 g of s into h of s. And we know that what is this limit s tends 0 g of s into h of s? In the previous equation, limit s tends 0 g of s into h of s is kp. Okay, so we can just substitute the value of kp here. So that is the ESS will be equal to 1 by 1 plus kp. That is for a if you are applying a unit step signal. Okay, for a unit step signal case, the steady state error. Okay, the steady state error ES will be equal to 1 by 1 plus kp, where kp is equal to limit s tends 0 g of s into h of s. Okay, and we know that already in the previous slides we have found that for a type 0 system, okay, the type 0 system will have a constant steady state error when the input is step signal. Okay, so that we are going to check here. Okay, so for a type 0 system, we are taking the an example of type 0 system. We are going to find the kp first. Okay, the kp first, because the input is unit step, so ES will be equal to 1 by 1 plus kp. For finding the ESS, we must know the value of kp. Okay, so kp will be equal to limit s tends 0 g of s into h of s, and normally we are representing the standard representation of g of s into h of s is like this. That is something k is a something like a constant. Okay, and the numerator will be function of that is zeros, and in the denominator polynomial the solution is poles. Okay, so s plus z into s plus z2 etc. by s plus p1 into s plus p2. This is a standard representation of a loop trans function, that is g of s into h of s. Okay, so here if you are applying s tends to 0, what we will obtain, that is k into z1 z2 z3 by p1 p2 p3, all this will become 0, which means it is a constant value. It is a constant value. So ESS will be equal to 1 by 1 plus kp. Okay, we know that ES will be equal to 1 by 1 plus kp. So here kp is a constant, so ESS will also be a constant value. So hence we can say that for a type 0 system, when the input is unit step, there will be a constant steady state error. Okay, that we have already learned here. That is, for a type 0 system, will have a constant steady state error when the input is unit step signal. Okay, so we can check what will happen for a type 1 system if you are applying a unit step. Okay, for a type 0 system, the steady state error will be a constant. Okay, so instead of that type 0 system, if you are taking a type 1 system, and if you are applying this step signal, unit step signal, what will happen here? Okay, so we are considering a type 1 system here, that is kp is equal to limit s tends 0 g of s into h of s. So g of s into h of s we are writing as a type 1 system. Okay, so here you can see there is a pole at origin, so it is a type 1. Here you can't see any pole at origin, so it is a type 0 system. Okay, so type 1 system is represented like this, that is in the denominator polynomial there should be an s such that the value of s is 0, that is the pole is located at origin. Okay, so here if you are applying s tends to 0, what will happen? The s is in the denominator, so s tends to 0 become infinity. Okay, that is, we know that something by 0 is infinity. Okay, so kp is infinity here. That is, if you are giving a step signal to a type 1 system, okay, step signal to a type 1 system, the kp will become infinity, and we know that ES is equal to equation is 1 by 1 plus kp, so that the kp is infinity here, so 1 by 1 plus infinity means it is 0, 1 by infinity means it is 0, so that the steady state error will become 0 for a type 1 system. Okay, so in systems type number 1 and above, for unit step input, the value of kp is infinity, and so the steady state error is 0. Okay, and next we are going to learn the steady state error when the input is unit ramp. If you are giving a unit ramp as input. Okay, so we are continuing the same steps. We are writing the ESS and we are substituting the value of R of S as 1 by S square because it is a unit ramp. So R of S will become 1 by S square, and substituting the equation we will get it as SS cancelled, so 1 S will remain here, that will go to the denominator, so S plus S into G of S into H of S. Okay, so if you are applying the S tends to 0 the first time, this is S only, so it will become 0, and the entire equation becomes 1 by limit S tends to 0 S into G of S into H of S. Okay, so limit is only applicable to this second time. Okay, the first time will become 0 here. So what is this one? Limit S tends to 0 S into G of S into H of S. We have already learned it as KV, that is velocity error constant KV. So ESS will be equal to 1 by KV for a unit ramp signal if you are giving unit ramp as the input. Okay, and also we are going to check for different type of system. If you are giving unit ramp signal for type 0, type 1, type 2 system, what will happen? Okay, so for a type 0 system, we know that the basic representation is like this, that is we are going to find the KV first. KV is equal to limit S tends to 0 S into G of S into H of S. Okay, so G of S into H of S can be represented like this, standard representation of G of S into H of S for a type 0 system. Here it is type 0, there is no S in the denominator, S set to 0. Okay, so if you are applying 0 here, S tends to 0 here, the term will become 0 because there is an S in the numerator. Okay, so if you are applying S equal to 0, the entire term will become 0. So we know that ES equal to 1 by KV in this case because we are applying a unit ramp signal. So 1 by KV, so that is equal to 1 by 0. So it will become infinity. So steady state error will be infinity for a type system. For a type 0 system, if you are applying a unit ramp input. Okay, and another case, if you are applying a ramp input to a type 1 system, what will happen? So just we are applying same equation we are writing, and the G of S into H of S is a type 1 system. So we are adding an S here. In the denominator part we are adding an S here for a type 1 system. So S and S will become cancelled, and we will get just K into Z1, Z2, Z3 by P1, P2, P3 by applying S tends to 0. Okay, so this is a constant value. So 1 by KV, KV is constant, so 1 by KV is also constant. So we are getting for a type 1 system, when the input is unit ramp, there will be a constant steady state error. Okay, that we have already learned in the previous slides. Okay, and we are still checking for type 2 system. What will happen if we are applying a ramp signal to a type 2? Okay, so for making it as type 2, we have to add an S square here. In the denominator part we have to add an S square. All of the terms are same. Okay, so S and S will be cancelled, so 1 S will remain here. So if you are applying S tends to 0, the denominator will become 0, and the entire term something by 0 is infinity. So KV is infinity here, therefore ESS will be 1 by KV is equal to 1 by infinity is equal to 0. Okay, so that's the case, and next we are going to check for a parabolic signal. Okay, so if you are applying a parabolic signal, what will happen? Okay, so first we have to derive a relation between the ESS and parabolic signal. Okay, so we know that the steady state error we have already written the previous slides. ES equal to the same equation, and substitute the value of R of S as 1 by S cube, and by cancelling then S square comes in the denominator part. So by applying S tends to 0, we will get as 1 by limit S tends to 0 S square into G of S into H of S. Okay, the first time will become 0, so the limit can only be applicable to the second time. Okay, so what is the denominator part? That is limit S tends to 0 S square into G of S into H of S is Ka, that is acceleration constant. Okay, acceleration constant. So Ka, so ES will be equal to 1 by K. Okay, so for a parabolic signal, if in the question if you are seeing a term that is unit parabolic signal is the input, then the relation between ESS and the static error is ES equal to 1 by Ka. Always it will be like this. If it is a ramp signal, okay, unit ramp signal, the relation is ES equal to 1 by KV. If it is a step signal E is equal to 1 by 1 plus Kp. Okay, so here it is 1 by K. Okay, and we are going to check for type 0, type 1, type 2 system like this. Okay, for type 0 system, if we are giving a parabolic signal, okay, so what will happen? So K, so we have to find the K here. Okay, K is equal to method S times 0 S square into G of sin h of S, and G of sin h of S for a type 0 system, we know that. So by applying S times 0, the Ka will become 0, therefore ESS will become infinity. And for type 1 system, K, okay, the Ka can be find as 0 here, because for a type 1 system, this G of sin h of S is written like this, so there is an S in the denominator, so S is cancelled, still S remains in the numerator. So if you are applying S times 0, it will become 0, ES will be equal to, again ES will be equal to infinity. Okay, so for type 2 system, we are adding an S square in the denominator part, so S square and square cancelled. So at last, if we are applying S times 0, we will get it as K into Z1, Z2, Z3 by P1, P2, P3, which is a constant value. So S equal to 1 by K, so 1 by constant, it will also be a constant value. So we know that for a type 2 system, when the input is unit parabolic signal, there will be a constant steady state error. Okay, and for a type 3 system, okay, for a type 3 system, the denominator part contains S cube. So when we are applying limit S tends 0, S square cancelled, and S will be there in the denominator, so the K will become infinity and ES will be equal to 0. Okay, so that's the case here. So you must remember that the main 3 points. Okay, that is, for a type 0 system, we'll have a constant steady state error when the input is unit step, and also for type 1, input is unit ramp, and for type 2, input is parabolic. Okay, so that's all. I hope all of you clear the relation between the steady state error and our static error constants. Okay, so thank you.